Question 3. Figure 4 shows the refractive index of a type of glass and how it varies with the wavelength of the light. So refractive index against light. Student says that it resembles the decay of a radioactive atomic nuclei with time and that it shows half-life behaviour. Well, comment on whether the student is correct. So the student isn't correct. For a start, most importantly, this isn't time here. So it can't be a half-life because that's not time. So that would be the answer that I would write down. So it is not half-life because the x-axis is wavelength, not time. So another reason why it's not an exponential decay, which is a better way of phrasing the question, not half-life behaviour, but an exponential decay, is that if it were an exponential decay, then in any given amount of time, it would have to always reduce by the same percentage. So if we think about this, it goes from 1.6060 in halfway along, which is there, it goes down to, what's that, 1.6035. So it's dropped by as that many, however much that is as a percentage. But in this time, or this amount of change in the x here, from there to there, it's reduced by a lot less. That reduction there is a lot less than that reduction there. And as a percentage of its original value, it should be the same. But this value here and this value here are almost the same. There's only a change in the fourth and fifth significant figure. So it should reduce by about the same amount. So if it were an exponential decay, with this as your scale, you'd expect it to look pretty much like a straight line at this point, actually, but it looks like a curve. It's because of the false origin here, which is why it might look like an exponential decay curve, but it isn't. Right. The dispersion d of glass is defined as the rate of change of the refractive index with wavelength at a particular wavelength d equals that. Determine the wavelength of 400 nanometers. Okay, so there's 400 nanometers. State an appropriate unit for your answer. So what we're trying to find here is the gradient, the change in y divided by the change in x. So the unit is going to be meters to the -1 because we're dividing by meters here. But let's do this first. So the first thing we need to do is to find the gradient. You may be given a mirror to do this, or you may just use a ruler. I'll show you both methods of how you do it. So what you need to do is you need to line up your ruler here and draw a tangent. So you need to move your ruler backwards and forward until you've got a nice tangent there. I think that's all right. Right, how do you do it if you've got a mirror? Well, what you do is you place your mirror like that. So this is the face of the mirror. And you rotate this around until when you see the curve, it looks really smooth and there's no cusp here. If you know that, then what you do is you draw a line like that, which is basically a normal to the tangent. It's 90 degrees to your tangent. And so when the line is nice and smooth, and when you look at the reflection of the line there, and this bit of the line's nice and smooth, you draw a line like that. Then you take your mirror off, you get a ruler, and then you draw at 90 degrees to the line you've just drawn, and that will give you a much better tangent than just doing it by eye like this. But not all schools probably will provide you with a little mirror to work out your tangent. Right, and then we need to work out the gradient. So there's no reason not to use the entire triangle here, because we need to use at least 8 centimeters for AQA, don't we? So 8 centimeters is there, so this will be big enough if we do the whole lot. So we've got, use a pen, d is equal to the change in n. So the change in n is this value minus this value. Well, it's this value minus this value really, isn't it? So it's 1.6020, take away where it crosses here, that's going to be 1.605, and I make that as a 4 there. And we're going to divide that by the final value here, which is 500, and if that's 550, that's going to be 555, isn't it? 60, 70, 575, yep, 555. Take away the start value, 300. Okay, now we've got to be careful because I've just messed it up because I've forgotten my units here. So that is times 10 to the minus 9 to turn it into nanometers. The units of that are nothing, there aren't any units of that. So here goes 1.6020, take away 1.6054 divided by, and then that is 255 times 10 to the minus 9 gives me this answer here, which is minus 13333. So I think it's 3SF. So minus 13300, and the units are meters to the minus 1. Why is that? Well, refractive index has no units and we're dividing by a wavelength, so that's meters to the minus 1. The mark scheme had this in the range of, it was 1.5 times 10 to the 4 plus or minus 0.2, so I'm in the range there, so we're good. Okay, it is suggested that the relationship between n and lambda is of this form here. You are to determine A by using a graph of n against 1 over lambda squared. So it tells you the graph that you need to plot. So this is going to be 1 over lambda squared, and the units of this are therefore going to be meters to the minus 2. And this has no unit. I think it's always worth, if something has no unit and you've realised, it's always worth writing that it's no unit, because then you're telling the examiner that you actually understand that it has no unit. Right, so I don't know why they've given you 3 columns here, but we need to work out 1 divided by lambda squared, and the units of that are meters to the minus 2. Make sure that you put your units in any column headings here. So we need to do 1 divided by 300 times 10 to the minus 9, so that's turning into nanometers, and square that like so. And we'll put this to, I'm going to put it to 3SF, so this is going to be 1, press ENG to make it into times 10 to the 12s, so I'm going to do 11.1 times 10 to the 12 there. Now when using a calculator like this, if we need to do lots of these, we can just press the back button and change that like so. So we got 8.16 times 10 to the 12. 6.25 times 10 to the 12. 4.9, just check that, that's a 4, isn't it, when it's rounded, times 10 to the 12. 4.00, make sure you don't just write that down as a 4, you've got to leave it to the same precision as everything else, times 10 to the 12. 3.3, and then that rounds to a 1, times 10 to the 12. And last but 2.78 times 10 to the 12. Okay, so now we have to plot these on here. So we need a little bit more space, so I'll just move that off to the side there and bring this in to the middle here. So we need to go from 2 up to 11, and we've got 1, 2, 3, 4, 5, 6, 7 major boxes. So if we say that's 0, that's 2, that's 4, that's 6, that's 8, that's 10, that's 12, and that's 14, then that will give us, we need to put a times 10 to the 12 in there, but that will give us enough room to plot it, won't it? Quite nicely, going up in nice numbers there. Right, so we're plotting this value against this value. So let's do this one first, 6.63, and we want 11, so I need a pencil now, get a nice sharp pencil. So be really careful when plotting, take your time. So that's 11, so that would be 11.2, so we want 11.1, so that's halfway between that and there, so it's a bit like that. I'm going to have to move this a bit closer to me. There we go. So then we want 1604.8, so that is 80% of the way from there to there, which is there. That is 1.6048, and we need that to be 8.16, so that's nearly 8.2, so it's just to the left of that there. These are quite tricky to plot. This one's a bit easier. There, 6.25, so if that's 6, that's 7, so that's 6.5, so 6.25 is there. So 7, 6.5, 6.25 is there. This one, 3, 5 goes here, so it's there, isn't it? And then we need to put 4.94, so there's 4, that will be 5. So it's just to the left of that. Okay, this one's a little bit easier, 4.00. This one is 6.28, so that again is there, 80% of the way between there and there, which is 16 boxes up, leaving 4 boxes, so that's 1.6028. And we want 3.3, so that's a third of the way along. As you can see, I've traded the rain from earlier for really heavy wind, so you're still probably struggling to hear me. And the final one, 6.25, is going to be there, 1.6025, sorry, and that's got to be 2.78. So there's 2, there's 3, there's 2.5, so 2.75 is halfway between there and there, so it's there. Oh, I've gone off the page. My apologies, I've gone off the recording there. So I think I'll just zoom in on those points so that you can see them a little bit better. You have to be very careful with your points. If you get any that are completely out of it, then double check them, because it's probably that you've plotted them wrong rather than that they're anomalies. So there you go. Okay, right, so now we need to draw a best fit line. Easiest way to do this is to turn the paper. Do not just join first and last points. That's not a best fit line, that's just ignoring all of the rest of your data. So you want, it's a bit difficult, this one, to see, you know, the points above and below, because it's actually, they're all very good. So you want to make it so that you've got a nice straight line going through, lots and lots of points if you can, but with an equal number above and below if you can. So there's one below there, 1, 2 above, and 1, 2, 3, 4 on. I think I'm happy with that. So I'm going to draw that in. Make sure you do it in pencil, so that if you mess it up, you can rub it out. Okay. Right, now we need to use this graph to determine what A is. Okay, let's go back to the equation here and write that back again over here. So n is equal to A plus B over lambda squared. So we're going to equate that to y equals mx plus c. And what do we get? Well, we've plotted the y-axis as n, and we've plotted 1 over lambda squared as x, which means that b is going to be the gradient and c is going to be a, so the y-intercept. So whatever the y-intercept is going to be our a. So let's have a look here. It's there, isn't it? So what is that? 2, 1, so it's that is 1.6015. So 1, 2, 3, 4, 5. So that's 1.6013. So it's the y-intercept, and it is 1.6013. It's got no units. Right. State the significance of A. Okay, it's a bit strange. When are you going to get A? So A is measured in the same as the refractive index here. So that's what A is. It's a refractive index. So when do you get A? Well, you get A as the refractive index when this fraction here equals 0. When does this fraction here equal 0? Well, when lambda is very big. So it's the refractive index for exceptionally large wavelengths. I don't see anything more significant about it. So it is the refractive index for very large wavelengths. Okay. Another suggestion for the relationship between n and lambda is this expression here, where c and d are constants. Explain how d can be determined graphically. Do not try actually do the graph, okay? Right, so what we need to do then is we need to use logarithms here. So this is another technique that you need to learn. So we're going to take logs. So we've got ln of n is equal to ln of all of this here. And this is this times by this, so I'm going to put the ln of c at the end, and I'm going to add that to the ln of lambda to the power d. Now you need your rules of logs here, so that's ln of n is equal to, and we can bring that power down there, so we get d ln of lambda plus ln of c. Right, so we're going to do y equals mx plus c. So that corresponds to that, that corresponds to that, that corresponds to that, and that corresponds to that. So here we go, we plot ln of the refractive index versus ln of the wavelength, and we're going to get a graph that looks a bit like this. ln of refractive index, ln of, and the units of this they like you to write are ln of meters. That has no unit. Okay, I really don't like this. That's no unit, but that's what AQA want you to write. And it's going to have a y-intercept of this, and it's going to be a constant gradient. So it's going to look something like that. There we go. And find the gradient, and the gradient will equal d. And d is equal to the gradient. Okay, and that's all we need to say there. We don't need to work out what c is, but I'll write it anyway. So to find c, you want to get the y-intercept, and then so you've got ln of c equals the intercept, so c equals e to the power intercept. Right, so that's not being asked for in this question, but they might ask that, so I've done that as well for you. But you need to just find the gradient, and the gradient is that. So when you take a log-log graph, these are perfect for figuring out power relationships because the gradient of the log-log graph is your power, which is there. Okay, and that is the end of question 3. I'm not going to do the option topics. There are too many of them. So I'm just going to leave it at that. Thank you for watching. I hope you have learned something. I hope it's been helpful. If it has, then please comment and like this, and tell your friends about it. And if you've got any more questions, then post them in the links in the comments below. Okay, thanks for watching.